research experience with you. I kind of prepared this lecture to touch on some key issues that I think are characterizing the contemporary water resources management. And as you can imagine, within one lecture of 40, 45 minutes, it's hard to kind of put everything in, but I hope to kind of send a message. My starting point in order to set the stage is this kind of interaction between the complexity, risk, and water being, in between. And I'm using a few pictures from the disaster in Japan, Fukushima power plant, and the earthquake, Great Tohoku earthquake, which created a pretty, interesting and complex set of interactions where water was playing the role through the kind of tsunami that created the damage, affected this very large nuclear power plant, and that, so many years after the event, we are still hearing and talking about the recovery and bringing the system back to some state relatively close to when it was at the time before the disaster. So there are so many issues in the kind of interaction. That's why I wanted to kind of talk a little bit today what we can do, what is the kind of research approach that my research group is taking at the University of Western Ontario in dealing with some of these. Water resources, like three key messages out of this lecture. I'm going to kind of show the slide at the end. This is instead of conclusion, so for those of you who may be slowing down after the lunch, these are really the key kind of points. I would like through the lecture and presentation to introduce a little bit different view on water resources management and consideration of the water resources as a social system. And I did that in a very large international auditorium once, and being a water resources engineer, I was really badly criticized by some of my colleagues, as you can imagine. But I'll try to provide the argument for this particular position. The second key message is that systems analysis, or the systems approach, is offering an opportunity to deal with the complexity. And Liana asked me to possibly use this lecture to introduce one particular simulation approach that is very well suited for dealing with the complexity, system dynamic simulations, and will be providing some kind of basic information on this particular approach. I hope for those of you who are familiar with the approach that this is going to be repetition, but I hope for those who didn't hear before that may be interesting. And the third kind of key message is that dealing with the risk assessment and management. And the message that I'm trying to send in this particular area is that considering the changing conditions that I think many of the very large infrastructure systems are exposed to, and considering the complexities that are coming from the interaction between different components of the systems and surrounding environment, uncertainty is going to be continuously present, and all the decision making in the future will be basically heavily, I think, heavily relying on our understanding of the risks and providing, as Stephen was pointing during our last meeting, or securing decision making under the good information about the risk. The very important part of the message is that I see that adaptation to these changing conditions as one, as a kind of way to take this risk into consideration, build it in our decision-making tools or decision support-making tools, and then kind of management of risk, use management of risk as one of the adaptation strategies. In dealing with the very complex systems and considering these future uncertainties, I think we have to consider both objective and subjective risks. So some approaches that are capable of integrating both are very, very important, and that's what I would like to basically convey. The difference between the subjective and objective risks is simply objective risk kills, and subjective risk is more or less related to perceptions and our value systems. And unfortunately, these perceptions and value systems are driving the decisions, because this is, we are electing people. People are making decisions more based on the, subjective risks than on the real or kind of objective risks. So my research is focusing on how can we kind of integrate them both and try to perform this risk management by having ability to deal with both of them. The lecture will talk a little bit about challenges, then I'll focus a little bit more on the systems approach, some really basic stuff on system analysis simulation. And I selected two examples for the end of the presentation to kind of illustrate some of these key messages. Let's start with the challenges. Number of them are probably quite familiar to everyone. We are facing pretty serious issues related to population and growth of the population, urbanization, migrations, the movement of people from areas where under different pressures to areas that are offering a little bit easier and or better support for kind of life. The population growth is now subject to these global changing conditions, and for example, you can read a lot how the climate change is creating a totally new ways of migration, how the people are moving from the regions that are subject either to serious droughts and not enough food, to areas where they can probably survive. The kind of migration paths that didn't exist in the past or were not so pronounced in the past. The second source of kind of complexity comes from the infrastructure systems, and I would like to point out both hard and soft infrastructure. The systems that you're very familiar, water, energy, transport, the communication systems, they're all becoming more and more complex, interconnected, and the failure of one or one part of the system may kind of propagate through the system very seriously, creating significant damage and affecting a very large number of people. On the soft side, we are talking about the complexity of institutional arrangements, industrial, social, culture, and other infrastructure elements that are all kind of playing a role. How we deal with for example, hard infrastructure, how we manage this hard infrastructure, and are we fully aware that the good soft infrastructure organization may affect the consequences on the management of the hard infrastructure? There are issues like globalization and the fact that nowadays the information is shared very fast. That the things that may be changing somewhere very far in the world. The example from my first slide, the tsunami in Japan affected the car factory in the neighboring city to London. In Woodstock, the Toyota is making, I think, RAV4, and due to the tsunami, the supply of the parts was not available, and the factory was closed for 3 weeks. So, very large number of people working in southwestern Ontario was basically functioning under the conditions that were thousands and thousands of kilometers away. On the kind of water resources side, we have issues dealing with the kind of demand and availability. The reason is simply the larger number of people demanding safe water for drinking. We have competing needs between the agriculture, the human use, industrial use. We have very serious issues dealing with the pollution and how much of the clean water we mobilize by disposing the wastewater into the clean body of water. Right now, the ratios are somewhere that one liter of the dirty water mobilizes between 8 and 10 liters of clean water if you only rely on the dilution as a process. The other option is to go with the treatment, which immediately brings into the process the cost and the other trade-offs that will need to be then kind of considered. On the availability side, we are talking about long-term change, like a change in climatic conditions. We talk about shorter-term variability, and still, and again, I would like to put the kind of pollution into the picture on this side, because I think the activities in the use of water are creating and impacting the availability. With this global changing forces, we are also seriously concerned with the extremes on both sides. Extremes of related to surplus of water and lack of water, floods and droughts. They are obviously propagating through the complex systems in a different way. From floods, we are trying to kind of protect ourselves. From droughts, we are trying to see how is the demand cycle being affected, and availability, and how can we deal with this. I think all these kind of points are bringing into the picture what I was talking about: uncertainties, risk management, and use of risk management as adaptation to deal with these issues. So this is part of my first message, or key message. And in this kind of consideration, I was asked to provide a discussion paper for Stockholm World Water Forum. Is organized every week. It's a very large international gathering of people and industry, almost everyone, governments and academia, everyone who deals with water in one or another way. And they usually prepare every annual meeting with some kind of key ideas, comments, writings, specially organized panels around these topics. And in 2009, they asked me to provide some input, and I did it. And in this particular input, I brought this idea that when you look at what we are trying to manage, when we are dealing with the water resources, basically we are really dealing with people. We are dealing with kind of both sides, and supply and availability and demand side. We are dealing with people, and therefore I kind of elaborated a little bit more here that we can look at the water resources systems as a kind of integration of 4 different subsystems: individuals, organizations, societies, then all of them kind of embedded in the environment. And these 4 subsystems are very much kind of interacting. They're connected, and they're connected with a number of flows, mostly the flows of resources and information. And in order to understand the behavior of these subsystems, the flows of resources and information are providing the kind of final outcome, how these different subsystems behave. What is, for example, what is the level of resources required for the functioning of each of the subsystems? And because they do involve people and organizations, the value systems are starting to play a very important role in the functioning of that process. And that's a kind of brief justification for this idea that really management of the water resources should be at least thinking about possibility of looking at the problem as a social problem, social management problem, not only the kind of physical or the natural science oriented problem. And this is where the kind of main disagreement comes. Many of people with kind of my education, and I suppose most of the people in the room are engineers, do not look at this problem as a social problem. We look at this problem mostly as a kind of either physical problem that we can find different solutions by building a piece of infrastructure or operating the infrastructure, finding out what are the natural the kind of natural forces or values that are involved in dealing with this kind of infrastructure, and then finding the management strategies that will be kind of operating. In that process, we kind of completely eliminate that. We completely eliminate these value systems, and if you look at it as a social kind of system, then you realize that values are essential for the behavior of the subcomponents, as well as the way how we can possibly manage them. The second key point is risk and consideration of this risk management comes as a consequence of the pretty high level of complexity and uncertainties, various uncertainties that are surrounding the water resources management. In this context, I'm talking about risk as a product between the hazard and consequence. Again, a little bit different context compared to traditional engineering view of risk, where we are mostly considering hazard, or we quite often equal the hazard to basically risk. If you try to use this simple equation, you realize that risk may have multiple dimensions. Assessment of the kind of reliability, resilience, robustness, in a way, how often the system fails, how fast the system recovers, what are the possibilities for functioning, with the partial level of performance and so on, may be considered in developing the proper risk management options. The second key point is this idea of the risk has two different sources, objective and subjective, or the kind of perceived, and that mostly the objective risk is characterizing the properties, or comes out of the properties of the real physical system, and it's of our concern, whereas the human decisions and political management decisions are being based on this kind of perceived or our beliefs in the different aspects of uncertainty. The final message is that risk management, in my opinion, is one way of adapting to changing conditions. And I don't think that this message is so strongly supported right now, but I think more and more we will be seeing that there is a definitely need in managing or finding out adaptation options, adaptation solutions, that we actually search for them within this area of defined different aspects of this.
I'm just curious, where does probability factor into your risk definition there? I'm curious to know, because oftentimes we'll define risk as a consequence that are likely to.
Usually you define the traditional definition of risk will be, defining it as a probability or the return period of some kind of event that disturbs the system.
And then the consequence of that.
And the consequence, but kind of looking at the hazard only, this is where the probability definition comes in. The consequence carries completely different dimensions. The consequence may carry, the monetary units. The consequence may carry various physical, non-physical, non-quantitative units. And the problem is how you multiply this probability with these different units. The example that I kind of selected to illustrate the process will give you at least one idea how this can be done. But this kind of formula is indicating this kind of going beyond just the probability of the unwanted event. Okay, let me now kind of go through this introduction of the systems approach, and this is, in my opinion, one of the very significant areas how we can deal with both the complexity as well as different ways of addressing uncertainty. The whole approach is very quantitative, I would say, and it's based on a very simple definition that system represents a collection of different parts that are kind of interacting together towards or to achieve a particular goal. So by this definition, we're making a considerable difference between these two, the pile of parts, and these parts kind of put together in the form of the vehicle that can allow you to, go from place A to place B, utilizing many of the subsystems that are functioning within this kind of vehicle. So by putting these parts together and defining the way how they interact, we are able to kind of build the structure that will, serve particular purpose. It is important to point out that the systems may include physical and non-physical components, and quite often we eliminate the non-physical components because of that mostly qualitative way of assessing them and measuring them. Origins of the kind of systems theory are from early 1920s in the area of kind of dealing with the research patterns. I really like this animation. This is the pattern of freezing. It's kind of occurring on the bubble, water bubble, and you can see how is the ice forming on the surface of that. So within this research in patterns, some very interesting findings kind of came out. The first one is that independently how different the ingredients of different systems are, they all are put together according to the same general principles of organization. And that kind of first finding in the early period of the application of the systems theory is leading to research in trying to find a generalized theory, generalized system theory that can be applied to every possible system, from naturals or human-made systems, from biological systems to that work didn't come up with a very finite outcome, and the whole area of systems analysis branched into kind of various fields, from fields of social sciences where so-called the systems thinking has been used as one way of looking at the world around us, to the area of engineering and manufacturing, and one of the probably most significant outcomes was the development of the computers, hardware, software, based on the general principles of system theory. The two probably most important implications are listed here. That the systems theory kind of provides really a way to deal with the real world problems, very large scale, complex problems. Provides also a way for people to get a good, clear picture of how the environment works. So in these two kind of implications, you will see that sometimes the systems theory does not lead, or application of systems theory does not lead to exact solution. How much water I'm going to release from the reservoir by lifting the gates under the particular flow conditions and the state of the storage. But actually finding the pattern, how the operations should be conducted under the dry or wet conditions with different levels of storage in the reservoir and so on. So the kind of this systems approach allows us to get a little bit at broader pictures, understand the patterns, move from the particular value that's usually characterizing one point in time, to looking the system behavior over time and understanding the kind of dynamics of the systems. So this is what kind of leads me to point out that among the techniques and tools that support systems approach, we have a really variety, very large number of options, from various simulation tools, very common in developing hydrologic model or hydraulic models, or some other examples you can come up with, to optimization tools that if we define particular objective functions, we can, by using particular mathematical formulations, identify the solutions that will either maximize or minimize these objective functions. Or if we are dealing with the multiple objective functions, identifying the trade-offs that may exist between various objectives within the system. So there are really variety of tools, and from very early, I think the Harvard program was probably the first since the late 60s, where the optimization, simulation, and other techniques were introduced in the water resources management, and since then being used all around the world. What I'm now pointing out here is it's a little bit different technique. This technique belongs to area of simulation, but it offers something pretty unique, and that's that kind of representation of the complex structures and the link between the structures, so the description of the structures and the behavior of the system. So this type of system, so-called the system dynamic simulation tools, are helping us to link the structures to behavior and allow us to use them for understanding how the complex systems function. The origins are 50s, MIT, Sloan School of Management. Professor Forrester was among the first names. In spite of the fact that he was trained as an engineer, he was teaching in management. And the system dynamics was introduced as a rigorous method for describing the system, facilitating the feedback analysis through the simulation, and finding the effects of the alternative system structures on the kind of control policies and the system behavior. Sorry. The implementation of this modeling kind of approach involves the process that usually goes through three kind of key important steps. The first two I kind of call the first step, where we identify what are the variables to be considered within the system structure, and then develop some relationships. They're usually called the causal relationships between the different elements of the structures. And then converting this into something a little bit more mathematical, that's called the stock and flow diagram, which is just a graphical interface to mathematical representation of the change of the state variables and the linkages between them. Stock and flow diagrams kind of function or require equations in order to and data in order to allow us to simulate and end up with the representation of the change of these state variables with time. So the kind of mathematics behind is not extremely complex and can be very easily described if you're talking about difference or first order differential equation and solution of it. But the kind of key point comes from the really philosophical view that's embedded in this particular approach, that the structure, focusing on the structure, focusing on building the structure is an essential step in understanding the behavior. And in order to link the structure and the behavior, we do that through the simulation. It is a little bit different way of looking at problems, and we are trained. I am participating still in the training of young engineers, and we are training them, but not using this kind of view of the problems. We train them mostly focusing on the subjects and the ways of already mathematically representing that and describing what's required in order to obtain the solution where the mathematical model of the system is there. If you take this particular approach, then the focus is much more on understanding, what are the elements of the system, understanding that complexity, also understanding that different links between the elements end up in a different behavior through this kind of so-called feedback relationships. So the causal loops or the causal diagramming is the first step in implementing this particular process, and that is nothing else than just linking the variables with the indication how they change when they interact. If they change in the same direction, one goes up and other goes up, then we call that positive causal relationship. If they change in the opposite direction, one goes down and other goes up, we call that negative causal relationship. And the importance of this kind of positive and negative causal relationships, or assigning the sign to a causal relationship, is that when you start building the structure, these causal relationships end up closing the loops among the various variables. And these loops are known as the feedback loops, where we kind of start with the state of the system, we perform some action on the system that as a consequence changes the state of the system. My favorite cartoon is here, indicating, that, introduction in the change of the system here is obviously going to, through the system, create a consequence that may affect this poor guy who initiated the process. The two types of interactions exist, or these feedback exist. And that's all. That's the whole theory. We have positive and negative feedbacks. In the positive feedbacks, the systems are being destabilized. They are not they don't remain stable. Any kind of change that's kind of going through this particular loop is pushing the system further and further away from the stable state. Negative systems, feedback systems, are something that we like a little bit more. They are stabilizing the systems. They are pushing the systems to a particular goal. An example of the negative feedback is the thermostat instrument on the wall, where you set the desired goal, the temperature, and that basically measures the state of the system, the temperature in the room, of the air in the room, and turns the furnace during the winter on and off in order to keep the system close to that particular desired state. The positive feedbacks are pushing the systems away from the stable states, and that's something that can be or has to be counteracted in the real world. Otherwise, the systems will create a lot of difficulties around us. So there are only two basic functional types of feedback, and we can very easily link that structure, the simple feedback structure, to particular behavior. This will be the description, this exponential growth or exponential decay. They are kind of illustrations of the positive feedback, how the system kind of goes away. This illustration will be the illustration of the negative feedback, where this line represents the goal, and the system behavior or the negative feedback is pushing the system towards that particular goal. The problem is they do not exist around us so nicely separated. The real complex systems include, thousands of feedbacks that are interacting, working together, nested within each other. And when they start interacting, kind of predicting behavior or understanding behavior is becoming very, very difficult. They say our body includes close to hundreds, thousands of feedback relationships that exist between different elements. This will be a very simple combination of the positive and negative, where you see the first part of the graph being dominated by the performance of the positive feedback, and then in the second one, negative feedback kicks in and trying and stabilizing the system. This is another way when we start combining multiple feedbacks together. They can generate oscillations into the system. They can generate some combinations of these kind of with oscillations, or they can produce something that's known as overshoot and collapse, but basically the system goes over the kind of desired state and therefore ends up in a collapsing state. So the message from here is there are only two feedbacks. Understanding them independently, it's very easy, but when they kind of get together, this is where the problems are. How do we discover what is dominating the behavior in one very complex system that includes multiple feedbacks? Development of the system dynamic simulation tools relies very heavily on these so-called graphical objects. They're known also as a basic building blocks. But basically, they are only illustrating or describing, the rectangles are describing the state variables or stocks. Flows are allowing basically stocks to communicate. So only flows can change the stocks. They either add or take out of the stock, inflows and outflows. You consider the stock to be the reservoir. The stocks carry the memory because they are showing the accumulations and they can go up and down. And then we have additional tools like arrows and auxiliary variables that help us actually describe now in more details how the structure of the system really looks like. By putting them together, we are creating the mathematical model because behind each of these rectangles you have a very simple relationship that describes the change of the system within the kind of time interval t, and as a consequence of the difference between the inflow and outflow. If we have obviously continuous, if we convert this to a kind of continuous equation, you will have a differential equation, first order differential equation. And that solution of this kind of mathematical problem is nothing else than basically the value of the stock over time. In modeling process, we go through the number of steps where we start using these building blocks to arrive at the descriptions of the systems, build the simulation tools, and allow through the simulation to investigate the behavior of the system. We start with the hypothesis, we test this hypothesis, we design different policies, we challenge the boundaries because every system that we usually build has certain boundaries. And then through the kind of iterative implementation of the process and different steps of the process, we allow learning to occur. So one of the key values of the system dynamic simulation is that really provides us with the insight in the system behavior, not so much prediction of the behavior and saying what is going to be particular value of the state variable in a particular time interval, but really linking the behavior over time and understanding the patterns, how the state variables within the systems are changing. To talk a little bit about now risk management, this will be a very brief review of the system dynamics simulation and one way or one particular tool that I'm strongly promoting as a way to deal with the very complex systems. This is an illustration how I would like to support with use of systems approach risk management. And this is a real example of developing the risk to municipal infrastructure of the City of London under the climate change caused flooding within this area. So from kind of assessing the inputs that may come from the climate models, downscaling tools and techniques, identifying the kind of the patterns of potential precipitation events, converting them through hydrologic model into the kind of flows, implementing these flows through the hydraulic model to find out the inundations. We are then able to get into this equation that I did show at the beginning, the basically hazard and consequences by using these floodplains that basically represents the quantification of the hazard with other information, physical, economic, and social to describe the consequences and integrate into one measure of risk that's here marked in the kind of different colors using as a spatial unit, so-called dissemination units, which are defined by the Census Canada as the smallest unit with the same population density. And the kind of you see these kind of steps that are describing the risk management problem as a system problem, allow the product of or generate information that can be now conveyed is in the form of where are the areas of particular risk, what is causing that particular risk, and possibly driving some decision making in the future. The map that you see here is, one climate change scenario. The City of London is 350,000 people, and the cost of the coloration on that map is approximately $800 million. And the infrastructure. That's it. We cannot deal with that. But when they have seen this map, they were extremely happy because they were able to kind of click on the dark red areas, identify what is really contributing most to the risk. Finding out that we have all the wastewater treatment plants in the floodplain, and if we do something to these wastewater treatment plants as a very expensive pieces of infrastructure, we can possibly reduce that risk a little bit. And now the work is progressing and actually implementing some ideas based on this evaluation. The second point is how to deal with this idea of dealing with the objective and subjective risks. And I did a considerable work in the area of fuzzy sets, which I think allows us to integrate subjective and objective risks together. The fuzzy sets are replacing, I shouldn't be saying that, but they are replacing the traditional probabilistic view and the probability distribution functions. And they are replacing it in something that's known as a membership function, which is the consequence basically of the qualitative assessment of the impact of the uncertainty. If you use these membership functions, and you can generate the assessment of risk by identifying the areas of overlap between, let's say, the acceptable level of performance and the system performance, real system performance, and identifying through the quantification of these areas the kind of level of risk that will include both, the objective and subjective uncertainties. Another way how we are implementing this is in another project that this is the reason why I'm in Vancouver. We have a very large project dealing with resilience of the large coastal mega cities to changing climatic conditions. And Vancouver is one of the 4 cities that this project is dealing with. Another 3 cities are Manila, Bangkok, and Lagos. And I developed the kind of approach that we are looking the broader impacts of sea level rise and flooding because all these 4 cities are exposed to these 2 types of hazard, through looking the impact on the so-called system performance, utilizing the system performance to kind of assess how fast the system will come back to either initial level or the level better than that, and converting this ratio of the lost performance to the required performance into measure of resilience that is value between 0 and 1. Let me quickly, I used more time than I was planning, but let me kind of quickly go through the 2 examples. The first one is, example from my earlier days. I was professor of engineering at University of Manitoba for 16 years before I ended up at Western in London. And at that time, I was working very closely with Manitoba Hydro, local utility, had a number of research projects. Most of the middle managers nowadays are my former students, I think, in Manitoba Hydro. When I go there, I feel like I'm entering the classroom. What we have done with Manitoba Hydro in this area of applying the system dynamics simulation, we were developing the model for the generation planning group. We also developed some tools of different nature, optimization tools that they're using in the operations. And we were modeling the kind of hydraulic sector, power generation sector, transmission and economic sectors as separate sectors that kind of work together in order to find out some answers relevant to maximization of the revenues, determining the kind of initial water storage in the lake. I know how many of you are familiar with the Manitoba Hydro system. It's a natural lake, Lake Winnipeg. Most of the major power stations are downstream on the Nelson River. And by regulating the lake using the GEMTEC station that you see here, the inflow into the lake, by simply regulating the lake, very large area provides considerable storage for power generation. So this is being very, very effectively used now in trade because the Manitoba Hydro system is interconnected system to Ontario, Saskatchewan, as well as US. And they're able to store the energy in the lake or in the storage, sell when it's more expensive, buy from the other jurisdictions when it's cheaper, and make considerable money for the province in that particular way. So using these are the type of, we call them spaghetti and meatball diagrams, which are showing the kind of system dynamics model. In the middle, you will see the kind of Lake Winnipeg, and then this is the hydraulic sector, this is the generation sector, these are different power stations. And we were able to kind of capture, describe the structure of the Manitoba Hydro system, and then they were very much interested in a wet and dry kind of scenarios for the planning purposes. This was done for the planning department, where the kind of interactions between the storage in the lake, generating capacity, and energy demand were kind of simulated using the model. And I'll finish with just quick introduction of the Coastal Cities at Risk project, and where we are using this resilience that I mentioned as the basically system product of the interaction between the impacts that sea level rise and flooding may have on the larger coastal cities. We have a very interdisciplinary teams and considering 5 different impacts: social, health, economic, and kind of organizational, and physical, obviously, impacts of inundation and so on. And they're all put together through the interaction between the system dynamics model that deals with the dynamic character of the impact and the spatial distribution of the GIS, where each location in space is now considered as one of the decision-making points where the impacts can be analyzed, and in that way, basically, very dynamic maps of resilience generated for the municipalities. These 4 cities are developing these models based on this principle of spatial dynamic resilience, and this is just a simulation of the kind of calculation that shows you what kind of results we can produce to this type of risk analysis. First, we can have this kind of resilience representation. This is time. This is the measure of resilience between 0 and 1. This is just a very schematic representation of space, where now each location in space is one of the decision-making points, where we can now find out in the form of the map how will the kind of resilience change with the progression. This will be the moment when, let's say, the flood hits the city. This will be the loss of performance, either combined 5 impacts or for each of the impacts that I said, for example, health or physical and so on. And this is now the consequence in space on the changing kind of resilience. What you see is other functions here are so-called adaptive capacity functions, and they are describing, what are the tools that we have in order to kind of manage or affect that resilience. If you're talking about health resilience, for example, how many doctors, hospitals, where they're located, what are the type of services that can be provided in the case of injured people or people affected by the disaster. To repeat at the end my key kind of message, I was trying through this to illustrate an idea of looking at the water resources systems as social systems. I was trying to provide you with a little bit of insight how systems approach can be helpful in dealing with these water resources systems, and also point out that risk assessment can be used as a really adaptation to changing conditions by considering 2 important things. One, way of integrating objective and subjective uncertainties, and another one, dealing with the way how to capture the response to complex system structures. I'm sorry I took a little bit more. I was planning to give us a chance to discuss or answer some questions. I'll be very happy to do that. Thank you. Any questions, comments? Yeah.
On your spaghetti and meatball dynamic representation, are you doing the step like in the systems work that on funding elsewhere, where you're putting in the human dynamics? Are they're all part of that spaghetti and meatball?
Yeah. In this particular example, in the Manitoba hydro example, we had only one sector that dealt with the demand. So it was a kind of integrated human or the changing conditions. At that time, the planning department, using the kind of longer term simulation and main focus on putting the system through the situation, let's say, of insufficient water supply and what the system should do or how it should adjust. They were not so much concerned in the operational questions and the role of the, let's say, human error or something like that. For the operations, we did actually develop a number of, I didn't bring all the examples. We had a very interesting example. For example, how you operate the GEMPEX station during the freeze-up period, because that determines the power production during the winter. And that was purely driven by an expert, human expert. So we worked with the person to kind of understand, the way and the reasoning how this was done, and then we built a small kind of system to assist in that process. The key message is that the approach is equally capable of capturing the physical and non-physical aspects of the system. In fact, modeling the human behavior, human performance, as well as the kind of physical characteristics of the system, and let's say natural characteristics of the inflow that may be affecting the system. Yes?
Happy to see that you're promoting system dynamics. When I did my master thesis, I used system dynamics to look at the water sector. I enjoy doing that. It's very useful as well. I have a question on your views. You mentioned that briefly, and I think you mentioned it in your book, the chapter from probability to probability.
Yes.
How much peer support do you have?
Peer support?
Yeah.
It's a tough question to answer, but I must tell you, I get it quite often. Not too many people are accepting, let's say, in practical application the fuzzy set theory. But on purpose, the book is very lengthy, it's 600 pages, but I devoted a whole chapter to that, and I illustrated all the system of simulation, optimization, multi-objective analysis in the fuzzy environment, just trying to basically convey the message that we have some theoretical background to deal with these subjective risks and bring the subjective risks into the decision-making process. When I talk to decision makers, when I talk to the people, I see the acceptance of the idea, but in practice, I think there is a lack of knowledge. And I must tell you, I am not teaching that. For example, we don't have a course in the civil engineering curricula where, for example, the fuzzy set theory is being introduced. I do use portion of my graduate course to, convey some ideas how you can use fuzzy sets, fuzzy definitions to come up with the risk. But we do not have that yet as a kind of really mainstream thing.
Yeah, fuzzy set theory is very useful for
theory is old.
control engineering.
Theory is very old, but it's really not yet fully. I have a very strong feeling it will come. It will come, and it will come from the fact that we are more and more aware of the fact that there is a considerable difference between the objective and subjective risk. I was working in the Red River after the very large flood of 1997, flood of the century, and we realized that all the pressures that were coming on the politicians, local politicians, and then to the province and everything, were driven by the perception of the flood. The people who lived through the flood, and I was also aware to learn how these perceptions are changing with time. First time we went into the valley immediately after the flood and said, you are engineers, you know what, we'll listen to what you say. 2 months later, we come with the final report, come up with the recommendations that the valley will be subject to similar floods in the future. The same people, the mayor of a very small city, Morris, was telling me, you were maybe too strong in your language, saying, that there is a potential risk that may affect people who would like to come and live and, develop. So you see the change over time, and it's a problem with human nature. We are trying to forget the bad things and, go on with the life. So I think we need to have ability to bring that into our tools and assessments of different options, different alternatives, even structural or non-structural measures that can be used to deal with the problem.
But still, when you look at flood management measures and crop protection and whatever you're going to do for the users of floods, for instance, you have to look at the economics.
True.
But you already theory of
But you can actually combine that, and I think that's my main message. You can actually combine through the fuzzy set theory. You can kind of combine the quantitative, or the assessment of the objective is together with this, more subjective aspects.
So is subjectivity modeled at all? Whatever you do. I haven't read your book, but it looks like, subjectivity is extremely important. from what you're saying. So,
In this particular aspect, I was just trying to point out that we have a very significant component in the, in the risk management that deals with the subjective, with the subjectivized.
that's taking
But it's not the only. It's definitely not the only. This is why I'm saying the kind of integration of objective and subjective is. And I found that Hudson theory is really supportive, so that it provides for that integration.
Could you touch a little bit on how would you assess or measure human behavior when it's in mass? Like, it's London city, but so how would you, simply how would you convert human behavior, reaction or action, to your
It will take me too much time, but
just
I can tell you, for example, for the city of London, if I can. Oh, I forgot to show you this picture. I have to show you this picture. This is the picture of my son taking a picture, and this is basically on the Lake Winnipeg. That's being right now operated with the optimization model that's being developed in my lab. And the water levels that you see here are determined by that optimization model. So this is why I really like this picture. In this example, how you bring that, for example, these membership functions are assessed by talking to people. Talking to, you can do it with an expert, single person, you can do it with a group of people. So they are representing, in a way, the projection of the behavior, how the people see the, problem. So this is, let's say, the kind of flood. This is the particular flow that characterizes the flooding conditions. And it will tell you, how this particular group of people that's modeled with this triangle responds to that. So what is the meaning of, 55 cubic meters per second for that? For you, maybe, one thing. For me can be very different thing. The people are saying, like, if you live through the flood, you have a completely different feeling, of the risk and way of assessing, reacting, responding than someone who never was exposed to that kind of disaster. So that's being collected, and there are procedures. In the book, there are different methods, actually, how you arrive at these functions, and that's being assessed directly through the communication with people. These we were collecting for the city, for example. We were talking to the expert in the city in order to find out and use them in that risk assessment.
Does that mean that when you're doing work and you're combining the subjective and physical systems, you may conclude that it's more cost effective to educate the population on basically what real risk looks like, so it's sort of that change in the perception of what is.
It's not so much to educate, it's much more to bring that information, how the people perceive risk, into your decision making. So, like we use as a standard particular return flow period for designing a dike. So, if I tell you 1 in 250 years, you know what's the meaning of the probabilistic terms. Probability every year of 1 over 250. That's based on the data that we have. We process the data, we calculate the probabilities, we find that probability. So that's the constant. But when you talk to people and you use that value of flow, they have a very different reaction to that. So my point here is that we try to combine these two pieces of information if you're designing the dike or improving or maintaining the dike in the future.
So does that mean that your models change over time? Perception will change over time. So are you constantly reiterating?
Okay, this is not yet, kind of fully integrated. What I'm talking here is mostly on the integration of this subjective and objective uncertainties. In the simulation, I was talking more about the behavior of the system and how the system can change. It could be possible, but the decisions are being made in a certain point in time. And this type of risk analysis is kind of feeds into the decision-making process. And the simulation of the system behavior is much more of interest if we are trying to understand how the complex system functions. Okay.
Yeah, do you have is there any interest from countries as a whole to apply this system approach to their water management? The point that sticks out in my mind is a few years ago, BC Hydro had Wynne Dyer, who's a quite a famous journalist, come give a presentation. And I think the thing that stuck out in my mind on that was he said you should sell water to the States before they kick the door down and take it. Now, Canada has policy banning bulk water exports, but I imagine this sort of system approach is being taken, and whether it's North America as a whole or Canada and the United States, and these conversations.
In many aspects, I think the approach is already kind of in practice. I mean, you guys are running optimization models, you're running transfer simulation models. So I would say, within the utility, you have a considerable use of the systems approach. Now, at the level of the country, and making these decisions like international decisions, Red River, the flooding that I was describing, is an international river. 90% of the watershed is in the state. The river flows north and affects, Winnipeg and Manitoba and floods everything down there. So I think from case to case, from problem to problem, the systems approach is being used. I'm not kind of fully aware where the, let's say, whole national policy is being based on that. But I had a project, a strategic research project, to develop the tool for our federal government. We had 6 different federal departments to provide them with assistance in making policy related to climate change.
Because
you are fully aware how strong is our policy on climate change.
Well, because Wynne Dyer's point was that regardless of what government was saying, their military was actively doing this.
Well, that's a very single problem of the kind of water supply and water transfers, and I see tremendous value. You can very easily apply, some system tools to look into this problem and so on.
To the best of your knowledge, has there been an attempt to take working simulation model with a graphical interface to a town hall meeting in front of educated people and show them, like, playing with those variables, you go ahead and rather not make
U.S. Army Corps of Engineers had, for example, a very lengthy process that they were building this type of tools, like gaming tools, and bringing them into town halls for people to build them on, to identify what are the key elements, what are the issues, putting them together, and then simulating to see, the consequences. Trying to support this kind of more interdisciplinary, so they were bringing, the biologists and the hydrologists and others in the room. So this is one. That was a pretty extensive program. It was going throughout the U.S. I know a number of what we have done, for example, for the City of London. We were I made tons of presentations, demonstrations from engineers within the city to a number of different committees responsible for, finally even the so-called committee as a whole, all the councillors and mayor and everyone else, kind of demonstrating, showing the simulations, how the risk is changing over time and so on. Yeah, there are many examples, many. The book, I did include in the book a number of examples that are kind of real applications. We should be probably finishing. Thank you very much for coming.